Ever used a compass and wondered why it points to the North Pole? The answer is related to the magnetic field of the Earth. In fact, our entire solar system is filled with magnetic fields from various sources. Let's take a brief survey of solar system bodies with magnetic fields to understand them better. We begin with Earth. At first glance, the Earth's magnetic field looks like that of a bar magnet in the center of the Earth, tilted by 11 degrees. But upon closer inspection, we notice that the field moves and changes with time. Little magnetic field patches, like the South Atlantic anomaly, march across the planet over tens of years. Based on studying the magnetic field recorded in the rocks and ocean floor, we know that the field has reversed multiple times. These features could not arise from a bar magnet in the interior of Earth, as the field would be constant in time. So if it's not a bar magnet that creates the magnetic field, what does? Dynamo action in the interior of the planet. Planets are hot inside. Just like a pot of boiling water, this heat causes the fluid part of the planet to convect. The convective motions of the electrically conducting fluid in the interior of the planet stretch the magnetic field lines and create new magnetic field in what scientists call alpha and omega effects. If the fluid motions occur in such a way that the newly generated magnetic field adds on to the existing one, then we have a working dynamo that keeps maintaining a planet's magnetic field over billions of years. On Earth, the conducting fluid that produces the dynamo is in the outer core, which is made mostly of iron, nickel, and some other light elements like sulfur. The same materials are believed to participate in dynamo action to generate Mercury's present-day magnetic field, which has been detected from space missions, such as Mariner 10 and Messenger. Mercury seems to have a bar magnet-like field that is slightly offset from the center. Not all planets have a magnetic field signature. We don't observe any magnetic field on Venus at present, and the rocks on its surface are too hot to have any record of past magnetic field. Other rocky planetary bodies such as Mars and our Moon show evidence of past dynamo action. The clues for this come from Apollo samples from the Moon, lunar and Martian meteorites, and space missions. So what happened in the past? How did their dynamos work? Why and when did they stop working? Scientists are still trying to solve this mysterious puzzle. As we travel farther out into the solar system, we encounter the gas giants, Jupiter and Saturn. Similar to Earth, Jupiter's and Saturn's magnetic fields look a lot like that of a bar magnet. Usually, the magnetic axis of a planet is tilted away from its rotation axis, which is what we see for Earth and Jupiter. But interestingly, for Saturn, the two axes are perfectly aligned, and we still don't know why. Jupiter's magnetic field is the strongest among the planets in the solar system. Over the decades, space missions like Juno and Cassini have provided us with a clear picture of magnetic fields of both bodies. These planets are huge and mostly made of hydrogen, which under high pressures becomes electrically conducting and is responsible for dynamo action. Flying further out, we encounter the ice giants, Uranus and Neptune. Voyager 2 measurements showed that heat is escaping the planet's surfaces kind of slowly, so the convecting fluid region inside of the planets is likely thin. They also showed that Uranus and Neptune have strangely shaped, not bar magnet-like magnetic fields, which suggests that the thin convecting fluid shells driving the dynamos are probably near the planet's surface. From fridge magnets to compasses to the deep interior of Jupiter, magnetism is at work in our solar system, shaping our daily experiences.